Hi everyone. From today, we'll talk briefly about some applications for electrochemistry and electrochemical engineering. We would start with battery, which is very common and we come across them almost on a daily basis. Batteries are electrochemical systems that convert chemical energy in solids. Pay attention to this word, in solids, to electricity by electrochemical reactions. I would like to emphasize this in solids because if it's in gas phase or in liquid, quite often we wouldn't call it battery, we quite often call it fuel cells. So it's a electrochemical system that converts chemical energy stored in solid to electricity or electrical energy by electrochemical reactions. And this conversion to electricity is its primary functionality. And of course, we may have so-called recharge battery, and in that case, you would also, during the charging cycle, going from electricity to chemical energy, again stored in solids. So these are the basic simple definition for battery. And the earliest battery probably appears in the 1800s. And one example would be called the Nile cell. The Nile cell, and we have mentioned this several times before in this class. And this is a schematic for a simplified Nile cell. Okay, on one side we have zinc, and it is the so-called negative electrode. Negative electrode. And for the zinc electrode, we have zinc and the zinc 2 plus ion, and there will be a so-called electrochemical half cell reaction, and quite often we write them in the reduction format, which means zinc 2 plus ion combined with 2 electrons to form zinc metal. Of course, this can be reversible. This half cell or electrode reaction can be reversible. When it's going through oxidation, um, half cell, then the zinc lose electron to form zinc ion. On the other hand, due to charging, during charging, the zinc ion would be combined with electron to form zinc metal. But generally, in this Daniell cell, we have negative electrode, and that is our zinc electrode. Okay, and if we check the standard electrode potential series table, we would find E0 standard electrode potential for this zinc 2 plus zinc redox pair, or for this um, electrode, the standard electrode potential would be minus 0.763 volt versus SHE versus the standard hydrogen electrode. Okay, because for the standard electrode potential series, we always compare to the common reference point, which is the standard hydrogen electrode. If you still remember, that is passing hydrogen gas onto platinum electrode, an inert electrode surface, into a aqueous solution that contains proton at standard activity. Okay, that is our negative electrode, zinc 2 plus, this redox pair of this half cell reaction, and it's negative in this Daniell cell. Then we would have positive electrode, and in this case it would be the copper electrode, and the so-called half cell reaction would be copper 2 plus ion combined with 2 electrons to form copper. Again, we write this half cell reaction in reduction format. That is quite often the standard case. We write it as a reduction half cell reaction. And similarly, the standard electrode potential for this copper 2 plus copper redox pair of for this electrode would be 0.337 volt versus again the same SHE, the standard hydrogen electrode. Okay, you get these numbers from the standard electrode potential series table. And as in the solution, this is copper metal inserted into solution that contains copper ion, and In reduction, copper 2 plus ion combine with electron to form copper metal deposit onto the electrode. Um, so this would be the negative electrode and the positive electrode. Of course, during discharging, the negative electrode would be so-called anode and going through oxidation reaction. During discharging, the positive electrode is going through reduction, and it would be called the cathode. Okay, during discharging, the zinc electrode would be the negative electrode, and it will be the anode where oxidation happens. In discharging, the copper electrode will be the positive electrode, and it will go through reduction to form copper. On the other hand, during charging, which is reverse of discharging, which is if we want to go from electricity back to chemical energy in solids, then in charging, the zinc electrode is still the negative electrode. But in this case, you are supplying electron into zinc electrode, and you reduce zinc 2 plus ion to deposit zinc metal. On the other hand, on the positive electrode, which is the copper electrode, you are stripping electron away from the copper metal to form copper 2 plus ion. That is what happened during charging process. So whether we are dealing with charging or discharging, the zinc electrode in this case is always negative. The copper electrode is always positive. So that's why in batteries or rechargeable batteries, quite often people only talk about the negative electrode, in this case for zinc, and the positive electrode, in this case for copper. Okay? And that is determined by the so-called standard electrode potential versus SHE. And then for a battery to operate, in addition to electrode, we need, as you understand, we need electrolyte. In this case, salts dissolved, in this case, aqueous solution to form aqueous solution dissolved in water, and zinc, the corresponding salt could be zinc chloride. For copper, the corresponding salt could be copper chloride, and both of these salts are dissolved in water. We have electrolyte that can allow conduction of ions, charged atoms, but not electrons or holes. Okay? And for practical batteries, for practical electrochemical system, other than this salts dissolved in water, quite often there could be so-called a membrane separator, as what we draw here, or sometimes a salt bridge. Membrane separator or salt bridge that separate the two chambers, the anode, the negative electrode chamber, and the positive electrode chamber, the zinc electrode chamber and the copper electrode chamber, to separate these two, and so that the zinc and the copper do not mix. Or you can achieve the same thing by putting these two electrodes in different container or glass beakers and connect them with a so-called salt bridge. They serve the same purpose, allow the ions to go through but without mixing, complete the circuit but prevent the mixing. Okay, and then we have the negative electrode, we have positive electrode, and the overall a full cell reaction. Remember, we can have two half cell reaction. To get the full cell reaction, the goal is to eliminate electron and maintain charge and mass balance. For example, for this half cell reaction for zinc, the net charge on the left is 0, net charge on the right is also 0. And mass balance, one zinc on the left, one zinc on the right. Similarly, for copper, the net charge on the left is 0, net charge on the right is 0. One copper on the left, one copper on the right. And for go from half cell reaction to full cell reaction, our goal is to eliminate electrons while maintaining charge and mass balance. And easily we can have zinc plus copper 2 plus ion to form zinc 2 plus ion and copper. And the mass is balanced, 2 plus on the left, 2 plus on the right. One zinc on the left, one zinc on the right, one copper on the left, one copper on the right. And I draw the arrow in both directions. As what we discussed before, zinc plus copper ion to form zinc ion and copper, and that is what people call discharge, going from chemical energy into electrical energy. On the other hand, if you want to reduce the battery, you need to so-called charge, going from copper metal and zinc ion into zinc metal and copper ion. You are spending electrical energy to store it in chemical energy. Okay, so that's a so-called overall full cell reaction. You get this full cell reaction by combining these two electrode reactions or half cell reactions, and with the goal to eliminate electrons. Okay, so a battery, we need negative electrode, positive electrode. We need electrolyte that prevent mixing and prevent electron shorting from in between, and quite often we need separator to prevent mixing. And we have two half cell reaction, and combined we have the full cell overall reaction. And then, as we learned before, the cell potential, especially so-called standard cell potential, when every species, especially ionic species, are at standard activity, while the solid, we treat their activity as one, then the standard cell potential, quite often we said it would be cathodic minus anodic. The standard electrode potential for the cathode minus standard electrode potential for the anode. The cathode is the one that is more positive, the anode that is one that is more negative. So we have 0.337 volt minus parentheses minus 0.763 volt, and the result will be 1.10 volt. This gives us a so-called standard cell potential. Okay, we have a simple denial cell or denial battery, negative electrode, positive electrode, electrolyte, and the standard electrode potential for the negative zinc, for the positive copper, and then the overall cell potential would be cathodic minus anodic, the more positive minus more negative, and then that gives us the standard cell potential. The O or represent it on the standard state. Okay, you may ask what happens if the concentration for the ionic species are not standard activity. That we will use Nernst equation to correct for non-standard conditions. That's what we learned before. Okay, and we just quickly refresh our mind when we do this battery introduction. This can be a simple battery. It has some basic components: negative electrode, positive electrode, and electrolyte. Of course, you may have membrane, you may have container, and other things. We'll talk about this in a moment.